Thanks for coming, everyone. I'm here today to discuss the new paper that I wrote a couple weeks ago and released, and I don't know if have all of you had a chance to read it yet?
Yes.
Okay, good. It's determination of mercury in water using our Jerome 505. So this is actually one of the instruments that I've been using. The method that I used was adapted off of the EPA method, 1631 revision E. If any of you guys want a copy of this, I have an extra copy. As you can see, it's rather lengthy. So what we did is, Garrett and I read through this and said, okay, where can we make improvements? And we took some liberties. The two big ones that we took were, this method describes a gold film track at the beginning. So mercury's evolved off, sits on the gold film. Gold film, you put some current through it, it comes off just like we do with a regeneration of our sensors, and then you have an atomic fluorescence detector. I think the reason that they do that is because that'll allow them to keep track of it's a little bit better sampling for stuff that's going to be sitting around. But if we want to take advantage of the portability, we can omit that step. So essentially what I wanted to do is make sure that we're not reading any mercury before the testing starts, and the only mercury that we're reading is the stuff that I'm asking it to read. So the first steps that I would do, I would check the calibration every Monday. So I'd go recalibrate the instrument if it needed it. It needed it once. The other 3 or 4 times that I checked it, it was fine. But before every test, I would take samples with the 0 air filter on it in the front, and then just to make sure it's reading 0. I had a limit of 0.1 or below for 10 samples in a row. Following that, I wanted to make sure that the glass that I was using was also clean. So this was the apparatus we used for testing. We fitted a stopper with a piece of glass, it's hollow, and then on top of it we just have Tygon tubing. We have an adapter here in the middle, which probably isn't required, but it has to do with the dimensions of this tube versus the dimensions of this fitting. So we needed some sort of adapter. We could probably stretch this tubing over it, but I didn't want to snap the glass and hurt myself. So this was inserted in the top. The other consideration that we have is we're using just a regular Buchner flask here with a vacuum fitting on the side, and we have clean air coming through. And so we put another filter on the side to make sure we weren't pulling mercury into the system. So this would help filter anything that was coming in. Once we did the blank checks, we'd put this on the front, completely empty. Now we wanted to make sure that the glass didn't have any mercury on the coat on the sides, and we have the same limit for this as we do the blank checks of 10 readings of under 0.1. One of the things that I found quickly was mercury is very difficult to remove once you put it into a system. So to clean this glass actually took quite a bit of steps. I'll go into that in a little bit. 10 samples of this. Then I would take the top off and we'd pour water. I was using ultra pure water in bottles. You can use deionized water. It just was easier to introduce this way. So for this experiment, this is how we did it. And I would pour 200 milliliters into this bottle, approximately. So somewhere around there. The consideration that you want to make sure is that you have some headspace between the bottom of your glass tube and the water itself. So that's, roughly 3 inches of space between them, and that's so that you don't suck up any liquid. It measures mercury just fine at that level. So I wanted to make sure there was no water or no mercury in the water as well. Same considerations that I had for blank checks and the glassware had to be under 0.1. The next thing I would do is I would take 1 ml using these syringes, these tuberculin syringes. I'll just give you a quick demonstration. And this is actually just water, but we'll call this the stannous chloride solution. So we had a prepared stannous chloride solution, which is used to reduce the mercury. And you just prep this, and then you want to put in 1 ml of stannous chloride into the solution. So, inject it in, sample again, and then this is going again. Usually for this one, I was just taking readings. I didn't have a limit that I was looking at. There's usually an initial spike of a reading of like 0.3 of a microgram per meter cubed, but after about 5 minutes it was reading 0 or close to 0 again. If it stayed there, I would probably have stopped the experiment, but it didn't happen. So this is good. This is pre-solution test 2. Everything's good. Still not getting any readings. I take a second syringe, and this is for the sample. Now we made 4 standards using this method, which describes how to make the standards for these. Now, what we were doing is we determined the total concentration in micrograms, doing just the math. So we wanted to see the total number of micrograms that we were measuring with the 505, because usually there's some discrepancies. Parts per million is a unit per unit measurement. A lot of times we wanted to do it's either grams per, micrograms per gram or milligrams per kilogram, and we're looking at volumes of water and masses of mercury. So we wanted to get rid of that. So we're just going to look at the total micrograms. And so the way that would vary is by the number of injections that I would do. So I would do a mil injection, that'd be 0.1 microgram. 2 mils, 0.2 micrograms. And so that's important because in the math, that's what we're going to look at. So this is the solution of mercury chloride, which we had prepared, and we'll just do 1 injection. So 1 injection, boom, done. Recap this. We can dispose of all the syringe material. We use new syringe material after every test. That's because the stannous chloride is a very strong reducer, and so it'll eat away at the tips of these, the metal tips of the syringe themselves. And the other one is because I don't want any residual mercury hanging out and then being injected on the next one. This would sample for about an hour, and then after that I would come in and look at it, and the results would be almost 0 again. So then I would go back, say, okay, it's done, and then I would make sure that the instrument itself can 0 again. I would disconnect it from the sampling vessel, reconnect it to the 0 air filter, and sample for another 10 minutes. This usually generated a graph. I don't know if you saw it, but it looks like an exponential decay. So you get a spike in the beginning, and then it just slowly comes down. So, and that's what we were expecting, because this whole thing works on an equilibrium principle where if, let's say, there's nothing happening here in the vessel, some mercury is going to go into the headspace and some of it's going to stay in solution. But as you're sweeping away the gas, which we're doing by having this pump work and pulling it out, you're going to continue to evolve all the mercury out. So it's trying to achieve this equilibrium, but you're not allowing it. So that's exactly what we were expecting to see. And then the other thing that we wanted to do is make sure that we had the test times about right. An hour seemed to work well But as you get into higher and higher concentrations, it's going to take it a lot longer to come out. And also you're going to start getting into problems where the range of the instrument is going to be challenged. So at a total number of 5 micrograms, we were seeing readings on the instrument of 85 to 86 micrograms per meter cubed. That's still in the low area. I mean, we're still safe there as far as the limits of the instrument's readings. But those are pretty high numbers for the 505. Once the instrument was done, we did all the plotting, and what we did was we took a summation of all the readings, and then we multiplied that by the flow rate, and then we divided it by 1,000 because of the conversion from milliliters to liters. And that would give us the total micrograms of mercury. And we, at the low end, were spectacular, you know, a couple percent. I talked to Glenn at the higher end, 6 injection, you know, 0.6 micrograms. We were looking at 7 or 8%. He said it's probably because the point between the 25 and the 100 during the calibration, it fluctuates. It's not as accurate as the 25 to 0 point. So, with that in mind, it does work better on lower end stuff. We did some sampling with some unknown concentrations just to see how it would perform. And as of right now, I can't say that it performed well or not because it didn't read any mercury. So maybe there was no mercury in the water. It's part of the unknown sampling thing. These were just known quantities. So if you do it right, it should recognize some mercury. Some of the things that you're probably going to get questions on are, do you get signals from the tin chloride to the acids? Are they corrosive and things like that? Some of the considerations that I had were certainly the acids. We're using hydrochloric acid and a strong reducing agent. And I found that the fitting in here, so if you take the nose cone off here, this was all fine until you get to where the frit and this nozzle are fitted together. That would start to rust, and if that gets if that rusts out from too much exposure, there is a slight problem. It'll start holding on to the mercury because you've got iron oxide sitting there, and the mercury will stay there, and you'll constantly not be able to zero. That's one of the reasons I checked for zeroing before and after. And that happened due to overexposure to the acids, I think. I did talk to Alex. There are some plastic fitting options we could go to if we really wanted to move forward with that. But we didn't get a signal. The other thing that I did to make sure that we weren't getting a signal from the mercury chloride solutions that we made was to do this same experiment with just mercury chloride, and it didn't provide a signal. So we're not seeing any of that. Did you guys have any questions for me as far as that goes?